More than 15 billion miles away, beyond the planets, beyond the Kuiper belt, beyond the protective bubble of our sun, a small machine continued to drift. Silent. Ancient. Alone. Voyager 1. Launched in 1977, when disco ruled the airwaves and computers filled entire rooms, this spacecraft was never meant to survive this long. Yet nearly half a century later, it is still sending signals back to Earth, faint pulses traveling for more than 22 hours before reaching NASA's deep space antennas. But recently, something changed. The data became strange. Glitches appeared. Signals grew distorted. Engineers watched as the oldest explorer humanity ever built struggled to speak clearly from interstellar space. It was as if the machine, standing at the boundary between the sun and the vast ocean beyond, was trying to tell us something before fading into silence. And that moment forced a powerful question. What have we really learned from pushing a spacecraft to the edge of forever? Voyager 1 is no longer studying planets. It passed Jupiter and Saturn decades ago. It has already photographed Earth as a pale blue dot suspended in a sunbeam. It has crossed the heliopause, the boundary where the solar wind meets the interstellar medium. It is now traveling through material that was born from ancient supernova explosions. In other words, Voyager 1 is no longer inside our cosmic neighborhood. It is in the space between stars. When its instruments flicker or transmit corrupted data, scientists don't just see technical failure. They see the physical limits of human reach. A reminder that distance is not just numbers on a screen. It is isolation. It is vulnerability. It is silence stretching across unimaginable darkness. And yet, even as Voyager struggles, humanity has not stopped looking outward. In fact, while one spacecraft drifts into interstellar night, another watches the birth of the universe itself. Because if Voyager represents the farthest we have traveled physically, the James Webb Space Telescope represents the farthest we have traveled in time. Voyager looks outward. Webb looks backward. One crosses distance. The other crosses billions of years. And this is where the story deepens. For decades, the Hubble Space Telescope gave us breathtaking images of galaxies, nebulae, and distant clusters. It showed us that the universe is expanding. It revealed that almost every galaxy contains a supermassive black hole. It transformed astronomy from theory into imagery. But Hubble could not see everything. There was a limit, a wall made of ancient light stretched thin by cosmic expansion. Beyond that wall lay the first galaxies, the first stars, the first moments after darkness lifted. We knew they were there. We just couldn't see them. And that is why NASA, together with the European Space Agency and the Canadian Space Agency, built something far more ambitious. They built a telescope designed not just to look far, but to look back to the dawn of time. The James Webb Space Telescope was engineered to detect infrared light. Unlike visible light, infrared can travel through cosmic dust. It can reveal objects whose light has been stretched, redshifted, by billions of years of expansion. In simple terms, Webb can see things Hubble never could. It can see the first light after the universe's dark ages. It can see galaxies forming when the cosmos was only a few 100 million years old. And when Webb released its first deep field image, astronomers around the world felt the same quiet shock. Those tiny smudges of light weren't just galaxies. They were ancient. Some formed closer to the beginning of time than anyone expected. Which brings us back to Voyager. One machine drifts outward into the unknown future. The other peers into the unreachable past. Both are fragile. Both are human. Both remind us of something unsettling. We are a species standing on a small planet, orbiting an ordinary star, in a galaxy of hundreds of billions, inside a universe of possibly trillions more. And yet we dare to measure it. We dare to cross it. We dare to understand it. But as Voyager's signal flickers at the edge of interstellar space, and as Webb reveals galaxies older than our theories predicted, a deeper mystery begins to emerge. What if the universe is not behaving exactly the way we expected? And what if what we're seeing, at the very edge of time, is only the beginning of a much bigger revelation, before it ever unfolded in space, it almost didn't exist at all. The James Webb Space Telescope was one of the most complex machines humanity has ever attempted to build. Decades in development. Billions over budget. Delayed again and again. Some critics even called it impossible. Why spend so much to look at light no human eye can see? Because that invisible light carries the story of the beginning. After the Big Bang, the universe was not immediately filled with stars. For hundreds of millions of years, it was dark. Hot gas cooled. Gravity pulled matter together. Slowly, the first stars ignited. Their light began ionizing the surrounding hydrogen. Galaxies started to assemble. Astronomers call this era the cosmic dawn. But here's the problem, that first light has been traveling for more than 13 billion years. As the universe expanded, space itself stretched. And when space stretches, light stretches with it. What once glowed in visible wavelengths has shifted into infrared. That is why the James Webb Space Telescope was designed differently from anything before it. Unlike the Hubble Space Telescope, which primarily observes visible and ultraviolet light, Webb is an infrared observatory. It does not see the universe the way our eyes do. It sees heat. It sees ancient photons that have cooled and stretched across unimaginable time. To detect such faint signals, Webb needed a mirror far larger than Hubble's. Its primary mirror spans 6.5 meters, composed of 18 gold-coated hexagonal segments. Gold was chosen not for luxury, but for physics. It reflects infrared light exceptionally well. But size alone was not enough. Infrared detectors must be kept extremely cold. Even the heat from the telescope itself could overwhelm the faint glow of distant galaxies. So engineers designed a 5-layer sun shield the size of a tennis court. Each layer thinner than a human hair. Together, they block sunlight and reduce temperatures to around -370 degrees Fahrenheit on the cold side. Webb doesn't orbit Earth like Hubble. It travels nearly 1 million miles away to a gravitational balance point known as L2. There, it can maintain stable temperatures and an unobstructed view of deep space. When it launched in December 2021 aboard an Ariane 5 rocket provided by the European Space Agency, the tension was almost unbearable. Hundreds of deployment steps had to occur perfectly. The sun shield had to unfold. The mirror segments had to align. One mistake could end the mission. But step by step, it worked. And when Webb's mirrors finally focused together as one eye, something extraordinary happened. The universe sharpened. The first images were not just clearer than Hubble's. They were deeper. Redder. Older. Where Hubble saw a faint smudge, Webb revealed structured galaxies. Spiral arms. Star-forming regions. Light that had traveled across nearly the entire age of the cosmos. And then came the deep field image. A tiny patch of sky, no larger than a grain of sand held at arm's length, exploded into view. Thousands of galaxies crowded the frame. Some warped by gravitational lensing. Some so distant their light began its journey before Earth even formed. Astronomers expected to find early galaxies. They did not expect to find so many. Some appeared surprisingly massive for such an early time in cosmic history. It challenged models of how quickly galaxies could grow. How did these structures assemble so fast? Was star formation more efficient than we thought? Or is there something incomplete in our understanding of the early universe? Webb wasn't just confirming theories. It was raising new questions. And that is the true purpose of exploration. Not comfort. Disruption. Meanwhile, as Voyager 1 drifts farther into interstellar space, its instruments measure plasma density and magnetic fields. It tells us about the boundary of our solar system. Webb tells us about the boundary of time. Together, they frame humanity's reach. One shows how far we have traveled physically. The other shows how far back we can see. And yet, as Webb peers deeper into the cosmic dawn, another mystery begins to form. If the first galaxies appeared earlier and more complex than predicted, what does that say about the timeline of everything that followed? Could the universe have evolved faster than our equations allow? Or are we only just beginning to understand the rules that shaped reality itself? For more than 3 decades, the Hubble Space Telescope was our window to the cosmos. Launched in 1990 by NASA and the European Space Agency, Hubble transformed astronomy from abstraction into imagery. It showed us pillars of gas where stars are born. It revealed galaxies colliding in slow, silent violence. It measured the expansion rate of the universe with unprecedented precision. Before Hubble, space felt distant and theoretical. After Hubble, it felt real. Its most iconic achievement came in 1995, when astronomers pointed it at what appeared to be an empty patch of sky. No bright stars. No visible galaxies. Just darkness. They stared at it for 10 straight days. The result was the Hubble Deep Field. Thousands of galaxies filled the image. Not in a crowded cluster. Not in a special direction. Just everywhere. It proved something profound: the universe is not sparsely scattered. It is overflowing with structure. But even Hubble had limits. Hubble sees mostly invisible light, with some ultraviolet and near-infrared capability. That works beautifully for nearby galaxies and objects within our cosmic neighborhood. But the deeper you look, the older the light becomes. And the older the light becomes, the more it shifts into infrared wavelengths. At extreme distances, the earliest galaxies become almost invisible to Hubble. It wasn't that they weren't there. It was that they had slipped beyond its sight. Imagine trying to hear a whisper, but the sound has been stretched so low it falls outside the range of human hearing. That is what cosmic expansion does to light. It stretches it. Redshifts it. Hides it in infrared. This is where the James Webb Space Telescope changes everything. Where Hubble saw faint red smudges, Webb sees structure. Where Hubble hinted at early galaxies, Webb reveals them in detail. The difference is not just sharper images. It is access to an entirely different era. When Webb focused on the same deep field region Hubble once studied, astronomers immediately noticed something unsettling. Galaxies that appeared faint and small in Hubble's images suddenly showed mass and complexity. Some seemed too bright. Too large. Too mature for their age. According to standard cosmological models, galaxies in the first few 100 million years after the Big Bang should be small and irregular. They should be slowly assembling. Yet Webb revealed candidates that look surprisingly developed. This sparked intense debate. Were these measurements accurate? Could early star formation have been dramatically more efficient? Or do we need to rethink aspects of our models about dark matter and structure formation? Science thrives on this tension. It is not about proving we are right. It is about finding where we are wrong. But Webb's power extends beyond ancient galaxies. It can peer into stellar nurseries hidden behind thick clouds of dust. In visible light, these regions appear opaque. In infrared, the dust becomes translucent. Inside, newborn stars glow softly, surrounded by swirling disks that may one day form planets. Webb has captured breathtaking images of the Carina Nebula and the Pillars of Creation, revealing star formation in unprecedented detail. Structures that once looked like silhouettes now glow with depth and texture. It is as if the universe removed a veil. And then there are exoplanets. Hubble could detect some planetary atmospheres, but Webb can analyze them with extraordinary sensitivity. By studying the infrared spectra of starlight passing through distant atmospheres, Webb can identify molecules like water vapor, carbon dioxide, and methane. For the first time, we are not just discovering worlds. We are reading their chemical signatures. And this raises a question that hums beneath every observation. If we can detect the building blocks of life in distant atmospheres, what else might be out there? Hubble gave us the scale of the universe. Webb is giving us its history, and possibly its habitability. Meanwhile, Voyager 1 continues its silent drift into interstellar darkness, a physical reminder of our smallness. Webb, by contrast, expands our mental frontier. One shows us how fragile our reach is. The other shows us how vast our understanding could become. But as Webb continues to send back images from deeper and deeper into time, scientists are confronting something unexpected. The early universe may not have been as simple as we once imagined. And if the beginning was more complex, what does that mean for the story of everything that followed? The image did not look dramatic at first glance. No blazing supernova. No spiral galaxy dominating the frame. No familiar shape to anchor your eyes. Just a scatter of light. But that scatter was a doorway. When the James Webb Space Telescope released its first full-color deep-field image in July 2022, the reaction was immediate. Scientists leaned closer to their screens. Astronomers around the world began adjusting contrast, measuring brightness, analyzing redshifts. Because hidden inside that quiet patch of sky were galaxies older than anything we had ever seen before. This was not just another photograph. It was a time machine. The light captured in that image began its journey more than 13 billion years ago. Some of those galaxies existed when the universe was less than 5% of its current age. Earth did not exist. The sun had not formed. Even the Milky Way was still assembling. And yet, there they were. Clear. Structured. Real. The deep field revealed something unexpected. Some galaxies appeared surprisingly luminous for such an early epoch. According to many models, early galaxies should have been small and chaotic, gradually merging into larger systems over time. But Webb was showing objects that seemed massive and bright far earlier than predicted. It was as if the universe had been building faster than we assumed. Astronomers began asking difficult questions. Were the first stars forming more rapidly? Were they larger and more efficient at producing light? Is our understanding of dark matter incomplete? Could our timeline of cosmic evolution need adjustment? The tension was not panic. It was excitement. Because this is what happens when you look somewhere no one has ever looked before. You don't confirm comfort. You uncover surprise. But the deep field image was only the beginning. Webb's infrared instruments allowed scientists to measure redshift with extraordinary precision. By splitting light into spectra, researchers could determine distances, chemical composition, and star formation rates. The telescope was not only capturing images, it was collecting fingerprints of the early universe. In those spectra, astronomers identified heavy elements, oxygen, carbon, neon, present in galaxies far earlier than expected. That means at least one generation of stars had already lived and died, forging those elements through nuclear fusion and supernova explosions. Think about that. Within a few 100 million years after the Big Bang, stars had already formed, burned, exploded, and seeded the cosmos with the ingredients necessary for planets and life. The universe wasted no time. And the deeper Webb looks, the more this pattern continues. Star-forming regions glow behind curtains of dust. Black holes appear in the centers of young galaxies. Gravitational lensing magnifies distant light, allowing Webb to peer even farther back than originally planned. It is as if every observation opens another layer. And each layer whispers the same message. The universe is more dynamic than we imagined. Meanwhile, Voyager 1 continues its outward drift, its power slowly fading. One day, its radio transmitter will fall silent forever. Its golden record, carrying sounds of Earth, will remain attached to a machine no longer speaking. But Webb is different. It is not drifting away from us. It is tethered to us, feeding us images from the edge of time. And those images are forcing humanity to confront something profound. If galaxies formed faster than predicted. If heavy elements appeared earlier. If structure emerged sooner. Then the conditions necessary for complexity, for planets, for chemistry, perhaps even for life, may have existed earlier than we thought. That changes the timeline of possibility. It suggests the universe may have been ready for complexity long before Earth formed. And that realization carries weight. Because if the cosmos built itself rapidly and efficiently, if stars ignited quickly and seeded space with elements, then the ingredients for life may not be rare accidents. They may be natural outcomes. Which leads to the next frontier Webb is already exploring. Not just ancient galaxies, but distant worlds. Worlds with atmospheres. Worlds with chemistry. Worlds that may, one day, answer the oldest question humanity has ever asked. Are we alone? As we gaze at the cosmos, it is impossible not to feel small. Voyager 1 drifts silently through interstellar space, more than 15 billion miles from home. Its instruments continue to measure magnetic fields, cosmic rays, and plasma waves. Its golden record carries the story of humanity into a void that may never answer back. Meanwhile, the James Webb Space Telescope looks in the opposite direction, not outward in distance, but backward in time. It captures photons that began their journey when the universe was barely taking shape. Every image, every spectrum, every data point is a message across billions of years. And these messages are startling. The early universe was not a slow, orderly process. It was a rapid, almost chaotic burst of creation. Galaxies formed faster. Stars burned brighter. Heavy elements appeared sooner. If the cosmos can assemble itself with such speed and efficiency, what does that say about our place within it? Humanity has always assumed the universe evolves on timescales far beyond our comprehension. But Webb is showing us that complexity arises quickly, almost as if the cosmos itself has an impatience for structure. And that leads to a profound reflection: if the universe can achieve such complexity on its own, then the seeds of our future, intelligence, life, perhaps even civilizations, may not be anomalies. They may be inevitable. We are witnessing a kind of cosmic humility. The universe does not wait for us to understand it. It existed long before our sun, long before Earth, long before life began. And yet, now, through Webb, we can see the processes that gave rise to everything we know, even ourselves. Exoplanets discovered by Webb offer another layer of wonder. Planets orbiting distant stars, some within habitable zones, others shrouded in clouds of methane or water vapor, are now being studied with precision unimaginable just decades ago. Every atmospheric spectrum is a hint, a whisper, a possibility. Could life exist elsewhere? The telescope cannot answer that question definitively, yet. But it provides the clues that might one day do so. And what of Voyager 1? Its lonely drift is a stark reminder that while we look outward and backward, our reach is still fragile. Humanity has launched objects into interstellar space, but we remain confined to one planet, orbiting one star, within one galaxy. Our tools, Voyager, Webb, and future observatories, extend our senses far beyond our bodies, allowing us to see, measure, and contemplate realities far larger than ourselves. The two machines together form a bridge across time and space. Voyager carries our past into the void, a message to whatever may someday find it. Webb returns images from the dawn of time, reminding us of the universe's incredible efficiency and scope. One drifts outward, the other peers backward. One shows our fragility, the other, our potential for understanding. And through both, a question emerges that humanity cannot yet answer: what comes next? As Webb continues to uncover galaxies older than we expected, as Voyager continues to send its final signals from the edge of interstellar space, we are forced to confront our own temporality. Civilizations rise and fall. Stars burn out. Galaxies collide. The universe is ancient and indifferent. Yet within that vastness, we find ourselves capable of curiosity, comprehension, and awe. Perhaps that is our greatest discovery. The universe is vast, violent, beautiful, and relentless. But we are here. We can listen. We can watch. And maybe, just maybe, we can understand our place within the story that began billions of years ago, long before Voyager, long before Webb, and long before Earth itself. As Webb reveals more of the cosmic dawn, and as Voyager drifts ever farther into the void, the universe whispers a warning and an invitation: pay attention. There is much to learn. And the story is far from over.